Hi, Physics 1. This is my second effort at the first part of the Chapter 13 slides. So I already recorded it once, but I realized that one ran very, very long, about 40 minutes. So I went into a lot of detail. So I'm going to post both that version, the long version, and this, the shorter version. Um, if you find this stuff interesting and you don't mind hearing me drone on and on, then go ahead and watch the long version. But if you've got other things to do with your time, then just watch this one. So again, the point of making this is to be quick, so let me just get started. So, what is the Big Bang Theory? We're going to be dealing with some very big ideas in this chapter. So, the Big Bang Theory, I'm sure you've heard of it before, not the sitcom, by the way. I despise the sitcom. More on that in the long video. But the Big Bang Theory, the actual theory, is this theory idea that approximately 13.8 billion years ago, the universe began expanding from a very dense, very hot state. It may, in fact, have been infinitely dense and infinitely hot, but we can't be sure because the physics that we have doesn't work before 10 to the minus 43rd seconds after the Big Bang. So, uh, if the Big Bang happened at time t equals 0, for the next, this tiny, tiny fraction of a second, our physics just doesn't work. We're trying to combine the general theory of relativity, Einstein's greatest idea, with quantum mechanics. And both of those ideas work very well most of the time, but when you try to bring them together in this very extreme situation, they just don't work. So, here is a timeline of literally everything that has ever happened. This is one of the reasons I love physics, is because we get to do timelines like this. So the way this works is all the way down here at the bottom. This would be time t equals 0. So this is the Big Bang. And yeah, for that first fraction, 10 to the minus 43rd seconds, you're going to have to do scientific notation throughout this chapter, by the way. Yeah, we don't know what happened. Our theories break down when we try to figure this stuff out. So we don't know what's going on there. So that is called the Planck error. So I went into great detail in the long video. Let me just do this one a little bit quicker. So on this timeline, time is running forward as we go up this timeline. And notice the scale is very logarithmic. So this first bottom third of this covers the first 1,000th of a second after the Big Bang. The next about a third covers maybe a quarter, whatever, covers the next 500,000 years. It's actually the next 380,000 years. So this chart is not perfect. More on that to come. And then the last part covers, the next 13.8 billion years. So 13.8 thousand million years is from here up to here. So yeah, very logarithmic. So yeah, if you want more detail on this one, go into and watch the long video. But yeah, basically, this is one of the reasons I love physics, because we get to deal with ideas like this and we get to make timelines that show literally every single thing that has ever happened. So on this timeline up here, this thin little ring up here at the top, this is the present. And if you were to drop down just a pixel or two, that would contain all of recorded history. So we're dealing with massive scales of time in this. And yeah, your entire life is just, all contained within less than a pixel high of this layer of this timeline here. So yeah, big stuff, big ideas here. So I've told you the Big Bang happened 13.8 billion years ago, and the universe started from a possibly infinitely dense, infinitely hot point. So I've got to back that up. So this is Carl Sagan. Hopefully you're familiar with Carl Sagan, a wonderful astronomer and popularizer of science. He did the original Cosmos series back in 1980. And he has this famous quote, this is sometimes called Sagan's razor, that extraordinary claims require extraordinary evidence. So this is a way of, it's a razor because it cuts out ideas that people present that they're not able to back up. So if you're making extraordinary claims like I am, you've got to back it up with evidence, because this is science. We have to have evidence for our ideas. So what is the evidence for this? I'm going to tell you about two pieces of evidence. And of the two, this first piece, this is the easier to understand. So the first piece of evidence is this fact that the universe is expanding, which we didn't always know. It was theorized originally by a Belgian priest named Georges Lemaitre. First looked at Einstein's equations of general relativity and realized that they suggest, well, perhaps the universe is expanding. And Einstein, no one really believed him at the time, including Einstein. Einstein thought that idea was crazy. But a little after Lemaitre came up with that idea, Edwin Hubble found the evidence for it. So yeah, it is Hubble, the man after whom the telescope is named. Actually, if you look, he died in 1953, so way before any work on the telescope actually got started. But yeah, he measured a lot of distant galaxies, measured what's called their redshift, and found that distant galaxies are moving away from us. And the further away from us they are, the faster they're moving away from us. So this is called Hubble's law. So this is the velocity at which the galaxy is moving away from us. It is equal to this constant, h naught, called the Hubble constant, times the distance the galaxy is away from us. So basically the idea here contained in this very simple statement is if d, the distance away, the distance from us to the galaxy starts to get very big, well, the velocity starts to get very big. So yeah, most galaxies are moving away from us, and the further from us that they are, the faster that they're moving away from us. So how is this evidence for the Big Bang? So on this scale, here's the idea of the Big Bang at the bottom, and time moves forward as we go up this. So if we're up here right now, and we're one of these galaxies, and we're looking at the other galaxies, and they tend to be moving away from us, what that suggests is that if we had looked earlier, if we looked yesterday, or 10 years ago, or 100 years ago, or 1,000,000 years ago, the galaxies, they're moving away from us now. So rewind the clock back in time, they must have been closer. So here we are, 1,000,000 or 1,000,000,000 years ago. The galaxies must have been closer. And rewind the clock back even further, and they were closer. And if you look at how far apart the galaxies are now and how fast they're moving, and run the clock backwards and do the math, it turns out that all of the galaxies would have been right on top of each other 13.8 billion years ago. So this is our first piece of evidence. The second piece, I'll try to do this quicker than I did it in a long video, but this is story time and this is interesting. So just hang with me here. So this is the Holmdel Horn antenna. It's in Holmdel, New Jersey, which is less than 2 hours away from the Charter Arts building. So the story is they built this thing in the 50s to basically get signals from our very first satellites. So they used it for that for a while, and then eventually they didn't need it for that anymore. So they let these two guys use it to do radio astronomy. So these guys said, great. So let me quickly explain what's going on here. So they're standing up in this platform. You see you can go up these stairs up to this platform, and then you can go up this other platform into this little room. So you see how this thing is like an open, it looks a lot like a cornucopia, basically, those things you see around Thanksgiving. But basically, signals from space, radio signals and microwave signals would come in this way, reflect off of here, and get funneled back up to here, and all your instruments would be up here. So your scientists, your radio astronomers would be up in this little room reading out the instruments. So these guys got to use this to do radio astronomy. And the first thing they needed to do was just kind of calibrate the machine. So they pointed this out at a blank region of space where they expected to find nothing. But instead of finding nothing, they found that there was a very weak little signal, which was surprising because they expected there to be no signal. The weak little signal, it's often called noise. So that was surprising. So they pointed at a different blank region of space, expecting to find nothing, and they found the same weak little signal. So everywhere they looked, they kept finding the signal, which they thought was pretty weird. So you'll realize Holmdel here on the map is fairly close to New York. So Staten Island, here's Manhattan. So they thought, okay, maybe there are radio and TV broadcasts coming out of New York, and our radio antenna is accidentally picking those up. So maybe that's what's causing the signal. So they pointed it intentionally in the direction of New York to see if the signal would increase, and the signal didn't change. So it wasn't that. So they took all the instruments apart and checked all the circuits and put it all back together. This is, the old-fashioned way of rebooting your computer, basically. They checked everything, turned everything back on, and they still had this weak little signal. So I've got to go into a little bit of detail here because this is just part of scientific culture, this story here. So you'll realize this thing is just sitting out here in the middle of a field. And different things will happen to something that's just sitting out in the middle of a field. So you can tell in this bottom right picture that, yeah, it gets snowed on and it gets rained on and wind and dust and leaves and things like that. All that stuff happens. But eventually they realized what had happened was birds were living inside of this. And birds do what birds do. They crap all over the place. So they went up inside the detector and they scraped out all of the bird crap. And they chased all the birds away. Now, the birds kept coming back, and they kept chasing them away, and the birds kept coming back. So eventually, they just shot all the birds. So that's what you do to keep the birds away. Kind of sad. People are always upset about that. And so they did that. So no more birds, no more bird crap. They went back into the little room, turned on the machine, and they found that they still had the little signal. So it wasn't the birds, it wasn't rust, it wasn't anything like that. They murdered the birds for no reason. So you can feel kind of bad about that. And then eventually, one of their colleagues said, well, we're pretty close to Princeton. I know there are some radio astronomers in Princeton working, radio astronomers working with radio telescopes. So why don't you talk to those guys and see if they have any idea? So the Holmdel guys, their names are Penzias and Wilson, they called Princeton and explained to them what was going on and how no matter what they did, they couldn't get rid of this weak little signal. And the Princeton guys knew right away what had happened. And the Princeton guys were a little bit upset because they realized that these guys had accidentally found really the smoking gun, the absolute clinching evidence for the Big Bang. Because the Princeton guys realized that if the Big Bang theory were correct, there should be this constant, it's called the cosmic background radiation, coming from every point in the sky. And the Princeton guys knew that the theory predicted this, and they had an idea of how big the signal could be, but they just didn't know any way of actually detecting it. Meanwhile, these guys out in Holmdel, so probably less than an hour away from Princeton, had accidentally found the signal and didn't know what was going on. So the Princeton guys knew that just an hour away, these guys had made this huge major discovery that the Princeton guys had wanted to make for themselves. So both of the groups, the Princeton groups and the Holmdel groups, or the Holmdel group, wrote up papers that got them published at the same time, where the Holmdel guys explained, the observation and the data they had collected, and the Princeton guys explained all of the theory behind it. So this was 1964. And eventually, it was 1978, a Nobel Prize gets awarded for this discovery. So who do you think gets it? The Princeton guys who did all of the theory, or the Holmdel guys who thought they had discovered bird crap? It is, of course, the Holmdel guys, the bird crap guys. So here's Penzias and Wilson. They won the Nobel Prize in 1978, and the Princeton guys got shut out. Now, real quickly, eventually, just in this past round of Nobel Prizes, one of that Princeton group did win a Nobel Prize. So some of the Princeton group had died by now because they were doing this work back in the 60s, but one of them is still alive and did win a Nobel Prize for all the work he had done in cosmology. But anyhow, I'm trying to go quickly at this. This is the whole point. These guys had found the cosmic microwave background. So this is the idea that everywhere you look out into deep space, you're going to see this background of light corresponding to a temperature of 2.7 Kelvin. So what does it mean for light to have a temperature? Well, if you're taking astronomy, if you remember Wien's law, this is the idea of Wien's law. So if you heat something up, like the range on, the heating elements on your electric range, you'll notice that when it's cool, it's not putting out any light that you can see. But as it starts to heat up, it starts to get a little bit red, and then it gets hotter and hotter, and it starts to get orange, and then eventually kind of orangey yellow, and that's as hot as that thing's going to get. So that's the idea of things at different temperatures put out different colors of light and different ranges of different colors of light. And this background that they had very closely matched what the Princeton guys had predicted, but didn't know how to find, a temperature of 2.7 Kelvin, so less than 3 degrees above absolute zero, a very, very cold temperature, but still, very importantly, not quite zero. So this is the earliest light in the universe. So this is not the light kind of exactly from the Big Bang from time t equals 0, because for the first 380,000 years, what was happening was the universe was so hot and dense that light couldn't travel anywhere. We'd say that the universe was opaque. So it took 380,000 years for the universe to kind of spread out and cool down enough that the universe becomes transparent and light can travel. So at that time, 380,000 years, we'll see the timeline again, and I think on the next slide. That's the earliest light we can see in the universe. And at that time, the light would have been very, very hot. So not 2.7 Kelvin, but tens of thousands or hundreds of thousands of Kelvin. But since then, in the intervening 13.8 billion years, the universe keeps spreading out and the light gets what's called redshifted. This is the Doppler effect, which is something that the astronomy guys also know. And I would go into detail, but again, I'm trying to make this video a little bit shorter. So here, I'll put links to this in the description. So here are a couple of videos about this, about the discovery. The second one, the Great Big Story one, is one of these guys. I forget which one is actually talking. I think they're both actually still alive. I checked last year and they were both still alive. But one of them talking about the discovery and coming across this idea that, let me just say this part quickly. Hubble did his work in like the 1920s and 30s. So since then, we've known the universe was expanding. People didn't right away accept this idea of the Big Bang. There was another theory at the same time called the steady state universe, which is actually a poorly named, or the steady state model, the steady state theory, which is poorly named because it did still account for the universe expanding. So the universe was changing, but whatever. Anyhow, Hubble's ideas from about 1930, first big piece of evidence for the Big Bang. But for the next 30 some years, it wasn't that widely accepted. And then when these guys made their discovery and the Princeton guys published their paper at the same time too, kind of right away, all astronomers and physicists, and the astronomers and physicists who study this kind of thing are called cosmologists. What we're dealing with is cosmology, the large-scale structure and history of the universe. Once these guys published their result, everyone right away jumped on board with the Big Bang theory. It wasn't even controversial anymore. So it caused a big paradigm shift. So from Hubble's time, 1930, some people liked the Big Bang theory. Other people didn't agree with it. And then once this idea came out, once this result was published, this discovery was made, and people realized, well, this is exactly what the Big Bang theory predicts, and they found exactly that thing. No one really doubted the Big Bang theory. None of the professional cosmologists. So this is not, among the people who study this is not a controversial idea and hasn't been for over 60 years. Having said that, in science, we always leave the door open. We don't prove anything. There's always a shadow of a doubt, but really no professional cosmologist or astronomer has really doubted the Big Bang theory. They argue about different facets of it and different things like that, and inflation and other ideas. But the general framework has been accepted cosmology for a very long time. So yeah, watch these videos. They're interesting. So baby pictures. Here is me on or around, I don't know if this was actually taken the very day I was born or a couple days later. So this is me on or around October 19th, 1976. I'm a bicentennial baby. So yeah, there's a baby Mr. Janowski. So this is a baby picture of the universe. So this is an image taken with a space satellite, I think it's called WMAP, of the entire sky. So if you've ever seen an image of like a globe, but it's smeared out in this big oval like this is the same idea. So this is the entire sky in all directions. And you'll see some areas are red. Well, these are a little bit hotter than the yellow areas, and those are hotter than the green ones, and so forth and so forth. So the red areas are the hot ones, and the dark blue ones are the cold ones. And the difference in the hottest temperature to the coldest temperatures in this image, how they measured the CMB, the cosmic microwave background, is just tiny, tiny fractions of a degree Kelvin. It's actually very, very close to being completely uniform across the whole sky, which brings up two very important cosmological questions, which I'm not going to go too far into because, again, short video. But one is, why is the entire cosmic microwave background across the whole sky so very close to being uniform, is the first question. And the second question is, well, why is it so close to being uniform but not exactly uniform? So in a nutshell, all the stuff you're seeing here, this is the earliest light in the universe, and the kind of structure and detail and different patterns you see here affect the way the universe evolved and the current shape of the universe and what's in it and where the galaxies are and where the galaxies aren't and all that stuff. So yeah, there's a huge amount of very important, very deep ideas in this picture. But I'm trying to make it a short video. So yeah, if you're more interested in this, you can watch this video too. I'll put the link there too. So yeah, this is the CMB. So on this picture to the left, where it says 500,000 years, it should totally say 380,000 years, because that is the point after the Big Bang. If you're looking at this graph, up until that point, the universe is so hot and dense that it is opaque. And essentially, you have nuclei, you have protons and neutrons joined together, and you have electrons, but they're separate because the universe is too hot for the electrons to be with the nuclei. But after 380,000 years, the universe has finally cooled off enough that the electrons can join the nuclei. We call this recombination, and that's what makes the universe transparent. So that's when light starts to travel through the universe, and when we look at this image here, that is the light we're seeing from 380,000 years after the Big Bang. So yes, wonderful, fascinating stuff. So there are four fundamental forces in the universe. They are the strong nuclear force. This does a couple things. It binds quarks together in the protons and the neutrons, and in the nucleus of atoms, it also holds the protons and the neutrons together. That's what the strong force does. There's also a weak nuclear force. The weak nuclear force, it turns protons into neutrons sometimes, and sometimes it turns neutrons into protons by messing with the quarks and flipping one quark from an up to a down, or a down to an up. And it sounds kind of weird, but this is how the sun works. The astronomy students know this. We studied this there. There's also the electromagnetic force. So yes, positive charges, or like charges repelling, opposite charges attracting, and north and south poles attracting or repelling each other. And basically all the forces in the universe that we deal with the exception of one, all the forces that we deal with in our everyday lives, with the exception of one, are actually the electromagnetic force. It's all electrons getting close to each other and pushing away from each other. So all of chemistry, it's all the electromagnetic force. And then the final force, take a guess, it is gravity. Gravity is the fourth of the fundamental forces. So we believe at this point in time that there are four fundamental forces in the universe. There's a kind of a fringe group right now that thinks they found a fifth, but that's not accepted science, and people don't really give a lot of credence to that. So maybe next year I'll have to update these slides. But at this point, we think there are only four fundamental forces in the universe, and every force that we deal with in one way or another is a combination of these forces. Not so much a combination. It's one of these forces. I could go into more depth, but keeping this one short. So on this table, we see all of the forces. And in this column, we have their strength as a fraction of the strong nuclear force. So what does that mean? Well, the strong nuclear force is 1 times as strong as the strong nuclear force. That makes sense. And the range of the strong nuclear force, this is far and away the strongest force that there is, but it has a very short range. It only works over 1 thousandth of a millionth of a meter. And beyond that range, it does nothing. But within that range, it is the strongest force by far. So that's the strong force. The weak force is far weaker. It is 1/10 millionth of a millionth as strong as the strong force, and it has an even shorter range. The electromagnetic force is fairly strong. It's only 1/100th as strong as the strong force, but it's far stronger than the weak force. And its range is infinite. So what that means is if you take two charges, two positives or two negatives, or a positive and a negative, and you hold them at different ends of the universe, they will still exert a force on each other because their range is infinite. Doesn't matter how far away you get, they're still exerting a force. The force gets very, very small, but it's still infinite. And then finally, you get to gravity. Gravity is the weakest force by far. It's only 1 over 10 to the 38th as strong as the strong force. So that's 1 over, let me do the math. That's 1 over 100 million times as strong as the strong force. The weakest force by far. And it also has an infinite range. So two masses anywhere in the universe always exert a force on each other. The force gets very weak very quickly as you start to get far away, but it's always something. It's never exactly zero. So if gravity is this tiny fraction as strong as even the electromagnetic force, why is it that gravity and not the electromagnetic force builds all of the big things in the universe? Gravity builds planets and stars and solar systems, and it builds the galaxies and the clusters of galaxies, and it causes all of these things to orbit each other and have their structure and everything. So why is this? Well, there's a couple reasons. One is that gravity has an infinite range. Doesn't matter how far apart the masses are, they're always exerting a force on each other. So, okay, that sounds good, but the electromagnetic force also has an infinite range, and the electromagnetic force is far stronger. So why is gravity the important one on the large scale? The reason is that gravity is always attractive. So masses always pull on each other. Whereas if you're dealing with charges or magnetic poles, like charges repel and opposite charges attract. So what that means is over the large scale, if you have positive charges somewhere and negative charges somewhere else, they'll pull on each other. But the positive charges will push on the other positive charges, and the negative charges will push on the other negative charges. So over big distances, the effect of all these different electromagnetic forces tend to cancel each other out because sometimes they push and sometimes they pull, whereas gravity is always attractive. Gravity is always a pull. So this chapter is mostly about universal gravitation. But we're not going to really start it now because we're just going to review. We'll start it a little bit next time. So try to remember, how long ago was the Big Bang? 13.8 billion years. What are the two main pieces of evidence that we have for the Big Bang? Well, the first one is the one that Hubble discovered, or got the evidence for. He wasn't the first one to come up with the idea. George Lemaitre was. But it's the idea that the universe is expanding. And the second one is the thing that the bird poop guys discovered, the cosmic microwave background. So these are the two main pieces of evidence. There are other pieces of evidence, but these are the two I want you to know. And finally, what are the 4 fundamental forces in the universe? The strongest one by far is the strong force. This binds the nucleus together, and it binds the quarks together in the protons and the neutrons. It comes with kind of a partner. The other one is the weak nuclear force. So this turns up quarks to down quarks and vice versa, and that turns protons into neutrons and vice versa. And that's what makes the sun work. The next force is the electromagnetic force. So this, everything you can think of that's electricity and magnetism, that's true. But notice also that, electrons are negative, protons are positive. So this is what holds electrons to the nucleus, which is how all of chemistry works. So most of the forces you'll deal with in your day-to-day life are actually manifestations of the electromagnetic force. With one exception, the other force you deal with all the time is the weakest force by far. It is gravity. So far and away the weakest force, and yet it builds all of the big things in the universe. So again, here is this table that compares the strength of the different forces to each other and their ranges, which I've explained before, and I'm trying to keep this short, and I know it's already getting long, so I'm just going to cut it off here. If you found this stuff interesting, watch those videos, maybe even watch the longer video I made. So hopefully you find this stuff interesting. These are the big ideas. This is as big as it gets. The large-scale structure of the universe, the entire history of the universe, all the big story, it's all here. So this stuff is definitely a reason to love physics. So hopefully you're finding this interesting.